All right, so let's take a look at the first lecture notes. All right. So in this lecture, let me know if you have any questions. Don't hesitate to stop. That's fine. So this lecture, lecture one, is about coordinate system. We're going to focus on three different coordinate system: the rectangular coordinate system, the cylindrical. I'm sorry, four different systems. Sorry. Rectangular coordinate system, polar coordinate system, cylindrical coordinate system, and spherical coordinate system. And we will learn how to convert from one system to another system using different formula. So again, the learning objective is describe a point on the graph using rectangular, polar, cylindrical, and spherical coordinates. Derive formula related to the coordinate system. When I say coordinate system, that means it is four. Convert point from one coordinate system to another, convert equations from one coordinate system to another. So let's start with something nice and easy. Again, for the first couple of weeks, we're just going to go over the materials that we see in multivariable calculus. All right, so let's talk about rectangular coordinate system. There's another name for that. It's called Cartesian coordinates. So I look into 2 dimensions in 3-dimensional cases only. So rectangular coordinates of a point are a pair of number written as x comma y in R2. Right. When you have 2-dimensional case, this is called a 2D plane. So right here, this is the 2D plane. You have a point on the x-axis, a point on the y-axis. You connect the x and y together, point on the x-y plane. Or you can describe this as R, a triple of number x, y, and z in R3. This is called the 3D space. So it's very straightforward to graph a point or to pinpoint a point on the 2D plane. It's a little bit more difficult, it's more involved when you want to pinpoint a point on the 3-dimensional space. So how could you do it? Here, to plot a point on the 3D grid, what you do is you move out from the origins. Along the x-axis. Until you get to the x value. So in this case, I want to use the example 1a. So 1 to point 1, -2, and so x equal to 1, y to -2, and z is equal to 3. So the first step is to move out from the origin along the x-axis until you reach x equal to 1. Right. And then start where you left off on the x-axis. And the next step is to move parallel to the y-axis until you get y equal to -2. So this allows you, this 3-step will give you a point 1 comma negative 2 on the xy plane. You follow me? Yeah. Now we are on the xy plane. So we start where we left off on the xy plane. So start where you left off on the point 1 comma negative 2 on the xy plane. And then the last step to get the z component is to move parallel to the z-axis until you get z equal to 3. So this is the general approach. You can just substitute x value, y value, and z value, and you get the same answer. Different answer for different points. Okay, so now let me go back to my coordinate system right here. So this is three-dimensional space, x-axis, y-axis, and z-axis. So x-axis is positive in this direction, y-axis positive in this direction, and z-axis is pointing upward. That's the positive direction. All right, so I'm gonna follow the instructions that we just wrote down to graph the point 1, negative 2, positive 3. So from the origins, I'm gonna move out to in the x direction until I get x equal to 1. So this is x equal to 1, right there. Let me zoom in a little bit. And then I'm gonna move parallel to the y-axis until I get to y equal to negative 2. So until I get to. So this is the point 1, negative 2. So now I'm at the point 1, negative 2 on the xy plane. Okay with that. And to get the z component, I'm gonna start at this point and moving upward, right, or downward. In this case, because we look at z equal to positive 3, so we're going up in the positive directions. So we're going up like this. Okay. The tricky thing about three-dimensional space is that things get tilted a little bit, so it's not exactly what it looks like, okay? So you're not exactly going up to 3, you're going up to a plane that is parallel to the xy plane, okay? And that plane is at z. So in a way, this look like this. So this is the point that we're looking for, 1, negative 2, comma 3. You okay with that? Does that make sense? Okay. Now let's try another point. Let me change the color here a little bit. So use red. Okay, so that's the point that we're looking for. So now let's move on to 1b. 1b, you need to plot the point negative 2, 3, and negative 5. Again, from the origin, you go out in the x direction until you get x equal to negative 2. So x equal to negative 2 is right here, right? All right. And from there, you move parallel to the y-axis until you get to positive 3. So you go into the right. Right, so you add the point -2, 3 on the XY plane. And from that point, you go down or move parallel to the Z-axis in the downward motion, because the Z component is equal to -5. Okay, so you move it down here until you get -5. Again, things not exactly the way it looks. What we do is not going exactly to Z equal to -5, but to meet up with the plane that is Z equal to -5. You would have that, right? And that plane is parallel to the X1. And this is the point, -2, 3, -5. And that's how you plot the three dimensional, a point in 3 dimensions on the 3-dimensional space. Any questions? Okay, so that's the coordinate, rectangular coordinate system. Are you okay with that? Yeah. Now let's move on to the next system. Is called the polar coordinate system. So this is also the 2-dimensional coordinates. Okay. But it's described this differently from the rectangular coordinate system. Am I moving too fast or good pace? Good. All right. So this point, 2-dimensional point, consists of 2 values, 2 components. The first component is r, the second component is theta. So r is the radius, right, from the origin to the point, and theta is the rotations. So let's describe that. So r, when you say r, you want to know how far you want to go out from the origins. And when you talk about theta, you want to know how much you want to rotate from the positive axis. So r, again, how far you want to go at. So this type of coordinate system is very useful for certain situations. When you ride an airplane, you use polar system. When you ride vessels, a ship, or a boat, you use polar coordinate system. Also, when you look at the globe here, they don't give you just the XY coordinate, they give you a degree, certain degree on the road, so that you can pinpoint the location of certain places. And those points are the polar coordinates. All right. So what you see on the graph here is called the polar graph. So this is still the y-axis on the vertical axis. This one is the x-axis or the axis. Right. So by conventions, the positive directions of the rotation is counterclockwise. Okay, so counterclockwise with respect to the positive x-axis. Therefore, we get definition. So here I have some point that we can play around with. So the first point is 2 comma pi over 4. So that means the radius is equal to 2 and theta is equal to pi over 4. So you have different circle on the polar graph. Each circle have a different value for radius. So the first circle is with radius 1. This is second circle is radius 2. Third circle is radius 3, so on and so forth. But you have to be careful when you look at polar graph because they may scale differently. But in this case, you have r equal to 2 and theta, which is the rotation, is pi over 4. What is pi over 4 in terms of degree? 45-degree angle, right? So 45-degree angle right here and is r equal to 2. So I get this point. Okay, so this point is 2 comma pi over 4. Good, so far so good. Now b is equal to -3 comma 2 pi over 3. So r is not really -3. It's +3, but you go into the other direction. Go to the opposite. In terms of degree, what is 2 pi over 3? One more time. 120. 120, yes. So 120 is over, is over here. And r is equal to 3. So let me zoom in. Use a different color here. So 3 here, right? But you go to the opposite side. So this is the point you're looking for. So -3 comma 2 pi over 3. And the last point is r equals to 4 and theta is equal to 5 pi over 6. What is 5 pi over 6 equal to? There we go. Very good. 150. So let me zoom in here. So for 150, so this is the point.
Just double check for negative radii, you go the opposite direction and that becomes your new starting axis to rotate.
I mean, that is different. But if you say the radius is 3 and theta is equal to -2 pi over 3, it's going to be the same thing. Any questions on example 2? Good. What time do we have to go? 12:15. So we have plenty of time. We have plenty of time, or we still have plenty of time. So two different statements, right? All right. So now let's find a connection between rectangular coordinate system and system. So I'm gonna look at the unit circle that you learned in pre-calculus already. The unit circle is described using the formula x squared plus y squared equals 1. So this is just from Pythagoras theorem. You know that? All right. So now I have a point on the unit circle, and the point consists of 2 components, x and y. So I'm gonna find a formula for x and y using the unit circle. So first, what I do is I do cosine of theta. So this is the angle theta. And I have the right triangle inside the unit circle here. So when I do cosine of theta, cosine is the adjacent over the hypotenuse. So you have x over 1. This gives you x equal to cosine of theta. Because of this, the horizontal axis is the x-axis or the cosine axis because of this. Okay. Now, when I do sine of theta, I have the opposite over the hypotenuse. Therefore, y is equal to sine of theta. Again, to emphasize that the vertical axis is the y-axis, but also sine. So this is just the unit circle from the unit circle. If we have a general case of a circle with radius r, center, and the origins, you may have a different formula. Okay. If we have a circle center at the origins with radius r, then the hypotenuse is no longer equal to 1, but is equal to r. So you have cosine of theta equal to x over r, or x is equal to r times cosine of theta. You understand where it's coming from? And then sine of theta is equal to y over r, or y equal to r times sine of theta. So I want to point out one thing to you, that the lecture note I have prepared very carefully. We're gonna see that I write how much space I cover. That means it means something. So if you get up to here, that's good. If you get up down here, that is not good. Okay. But I have a little bit of space on the next page, so don't worry about that. Now for tangent of theta, so tangent is sine over cosine, right? So tangent of theta in this case is equal to sine of theta over cosine of theta. So you have y over r divided by x over r is give you y over x. So in a way, we relate the rectangular coordinate system to the polar. So from here, we can derive one more formula. Okay. And the formula related to this Pythagorean theorem. So from x equal to r cosine of theta, we get that x squared equal to r squared times cosine square of theta. So what I'm trying to do is square both sides of x and both sides of y, and then substitute to the circle, the equation of the circle. And for y equal to r times sine of theta, we get y squared equal to r squared times sine square of theta. Then I'm going to add this two equations together. Get x squared plus y squared equal to r squared cosine square theta plus r squared times sine square of theta. And then you can take r squared as a common factor, and you're left with cosine squared theta plus sine squared theta. What is this expression equal to? 1. So that's the trig identity. So this is equal to 1. So you're left with x squared plus y squared equal to r squared. Or you have r equal to square root of x squared plus y squared. Usually when you take the square root of an equation, you have two values, positive and negative, but in the top. So in a way, you have four different equations or formula that relate the rectangular coordinate system to the polar coordinate system. So I'm gonna do 1, 2, 3. And then this is 4. Right, so 4 different formula relate rectangular coordinate system to the polar coordinate system. So that's two-dimensional system, right? So rectangular system and polar system. Now we're gonna move on to three-dimensional space, right? Using the information from polar coordinates, we add one more component to polar coordinates, and we get something called cylindrical. And cylindrical coordinate system is the three-dimensional system of r, theta, and z. The definition is going to be the same. That is, r is how far you want to go away from the origins. Theta is how much you want to rotate in from the positive x directions. And z is how high you want to go up or down. Okay. So this is a symbol extensions. Of the 2D polar coordinate system. To 3D space. And of course, obviously, this is the combinations between polar coordinate system and the z component. So again, r is distant from the origins. Right. Distance from the origins to the points. Theta is the rotations. From the positive x-axis. And z is how high you want to go up or how low you want to go out. How much you want to go up or down in the z directions. So my computer is about to run out of battery. Any of you have the charger? All right, so let's try the best we can here. All right. For cylindrical coordinate system, the relationship between the cylindrical coordinate system and the rectangular coordinate system is very similar to what we already see in the polar coordinate system. The difference is that we just need to add one extra component, which is the z component. So x, y is going to be the same. R x equal to r cosine theta. Y is equal to r times sine theta. And z just equal to z. Very straightforward. Now tangent of theta is equal to y over x. R again is equal to square root of x squared plus y squared. We just have an extra component of the z directions. Now another three-dimensional coordinate system is spherical coordinates. So this is three-dimensional point consists of three components, rho, theta, and phi. So rho, right, this one distant from the origins to the point. Theta is the rotation from the positive x-axis. And theta has to be between 0 and 2 pi. And phi is the rotation from the positive z-axis. And phi is restricted between 0 and pi only. So can you take a look at the graph here? This is the picture of the spherical. All right. So look at this point in red. So this distance in red is rho. Like you want how far you want to go out from the origins. And theta right here, how much you want to rotate away from positive x directions, and how much you want to rotate from the positive z directions. Now, how many of you is physics mean? Physics? Okay, so I would just want to point out one thing for you. There's an argument between physics and mathematics on the coordinate spherical system. So for mathematics, most of the time it gets used rho, theta, and phi. But in physics, rho and phi get swapped. Just the name is swapped. So it's a little bit confused when you read the math, the textbook in mathematics. Physics. Just want to point that out to you. But we in the math class, so let's stick with conventions here. The first component is rho, the second component is theta, and the third component is. All right, so I'm gonna build the relationship between the spherical coordinate system with the rectangular system. So what I do is that I'm gonna zoom out, zoom into this particular triangle. Okay. So this triangle here, 1, 2. Okay, gonna bring it over here. Okay. So this is rho. Gonna find into this rho. So this is V, this side is Z, find into this. And this dotted line right here is this dotted line. Okay. And this angle right here is the right angle. Okay. And here is also the right angle. It's the weird thing about the three-dimensional system is it's not really looking like right angle, but I can show it. That is actually the right angle. So this is the right angle. All right. So you agree with me on this, that the z-axis is perpendicular or orthogonal to x-axis and y-axis. You okay with that? Or more than that, the z direction is perpendicular or orthogonal to the entire xy plane. So anything on the xy plane will be perpendicular to the z-axis. Okay. So that means R, this one is R right here, is also perpendicular to the z-axis. Okay. So let me point that out. So this one is R. Okay. And Z is perpendicular to R. This two lines, this R right here, and this line right here, also R. These two line parallels, and Z is perpendicular to R, so therefore this line is. So this is R. So this part is Z. This is R, and you have rho. And now you have enough information to derive the relationship between the two coordinate system. So this is the angle phi. Now we're going to start with cosine of phi and then sine of phi. So for cosine of phi is the adjacent over the hypotenuse. So the adjacent is Z. The hypotenuse is rho. Therefore, you have Z equal to rho times cosine of phi. And for sine of phi, you have the opposite, which is R over the hypotenuse, or R is equal to rho times sine of phi. Now you have relate the z component to spherical coordinates, but what about the x component and the y component? Now we're going to use the information from the cylindrical coordinate and polar coordinate system to relate R back to, or x go to spherical coordinate and y go to spherical coordinate. But from the cylindrical coordinate, we get that. All right. So to make x appear in your equations, what you do is that from R equal to rho times cosine of phi, you multiply what on both sides of the equations to make x appear in the equations. Now okay. In a way, yes, but now x appear on both sides of the equation. So we don't want that to happen, right? So you start with R equal to rho times sine of phi. Now I want to make x here on the left-hand side. Let's go back to the cylindrical coordinate system a little bit and see what happened. So x is equal to what? R times cosine of theta. So what we do is multiply cosine of theta on both sides of the equations to make x appear on the left-hand side. So I do cosine of theta here, cosine of theta here. Right. And I get implies that x equal to rho times sine of phi times cosine of theta. And similarly, to make y appear on the left-hand side, you multiply both sides by sine of theta. So you start again with r times rho of sine of phi. And then let me use a different color here. You multiply both sides for sine of theta. And you get y equal to rho times sine of phi times sine of theta. So now you have x, y, and the last component is z. We already saw that earlier over here. Z equal to rho times cosine of theta, cosine of phi. So and z is equal to rho times cosine of phi. Now I have one more formula I want to derive. Any questions? Confusing? Okay, so far? Okay. So I have one more formula I want to derive here. That is, we're gonna show that x squared plus y squared plus z squared is equal to rho squared. Okay. So next we do. So x squared plus y squared plus z squared equal to, so here from this equation, we multiply with x square on both sides of this equation, square both sides of this equation, and square both sides of this equation, and then just add them together. Okay. And then I get rho square times sine square phi times cosine square theta plus rho square times sine square phi times sine square theta plus rho square times cosine square of phi. Now on the right-hand side, the first two terms, I will take rho square times sine square phi as common factor. I got rho square times sine square phi times cosine square theta plus sine square theta plus rho square times cosine square phi. And of course, the expression inside parentheses is equal to 1. And we left with only rho square times sine square phi plus rho square times cosine square phi. And rho square is a common factor again on the right-hand side. We got rho square times sine square phi plus cosine square phi. Therefore, at the end, you get x squared plus y squared plus z squared equal to rho squared. And that is the last equation I want to derive to make the connection between spherical. Okay, so I hope this gives you a good idea of refresher to the materials covering in multivariable calculus. Let me stop right here. I will see you next week, right? So there's no assignment at this point, but this is a good time for you to spend some time and think about the research topic you want. Okay. All right. Thank you everyone for being here. You have a good weekend.